Lesson on moving up and down. Warm-ups. A car moves to the left. It accelerates at 3 meters per second squared from an unknown slow speed to 30 meters per second in a time of 6 seconds. What was the original velocity? So let's first draw a picture here. And we have the car moving in that direction. Accelerates. We have an acceleration of 3 meters per second squared. Unknown slow speed. So V1 is question mark. It speeds up from that slow speed to 30 meters per second. So that must mean that the final velocity over here is 30 in a time of 6 seconds. What was the original velocity? So we're looking for VI. The equation that's going to relate all of that is going to be VF is equal to VI plus AT. Before we put in numbers, we got to figure out signs and if there's any kinds of conversions. We have leftward velocity, so this is going to be a negative 30. And in order for the car to speed up faster and faster at this direction, we're going to have a force pushing in the negative, so that means that the acceleration is also negative. So putting that in, we have negative 30 is equal to the unknown VI plus a negative 3 for the acceleration and 6 for the time. Add 18 to both sides. We get negative 12 meters per second is the initial velocity. Number 2, how long will it take an object to fall 6 meters? So we can have the time of fall equation. There, we start off with that. And we want to find time, so T stays a letter. The height of the fall is 6 meters. And G, remember we're just looking at plain old little g, so that's the positive value, 9.8. Type into your calculator 2 times 6 divided by 9.8 equals, didn't register. 2 times 6 divided by 9.8 equals square root 1.10. Number 3. An object falls for 3.9 seconds. How far does it fall? Again, since we have falling materials here, we can use the time to fall equation. The time is 3.9 seconds. We're looking for the H. G is 9.8. The first step is to square the 3.9. And we get 15.21. Since we squared both sides, the square root disappears on the right-hand side. I'm now going to take that 15.21 and I'm going to multiply by 9.8 and divide by 2. I get 74.5. And that will be in meters. Number 4. What does it mean that the acceleration of gravity is 9.8 meters per second squared? It means that for every second that passes by, the velocity is going to change by that much. And when we're talking about falling objects, the acceleration will always be a negative value. But please remember that little g is the positive value of 9.8 because that's used in so many different equations in different situations. And sometimes it's positive, sometimes it's negative in terms of the 9.8. So the letter G stands for the positive version, and if it's accelerating of gravity falling downwards, we'd make it a negative G, negative 9.8 there. Number 5. How fast is an object moving after 1 second of being dropped. Initially, it's going to be 0. After 1 second, it's going downwards 9.8 meters per second. After another second, I'm going beyond the question here. After another second, it's going to change by negative 9.8 to be negative 19.6 meters per second. And it just keeps on going, changing like that. So today's purpose, you'll learn how to relate our old equations to situations where an object flies up and then comes back down. And all of this time, it's going to be only affected by gravity. The relevance is that we can use our equations in situations such as a football being punted or a whale being blown up on the beach. Success. If given the initial velocity, I will be able to use equations to calculate how long an object is in the air. Tonight you should do, let's see, it's going to be homework 18. And the next quiz, it's not day 19, it's going to be day 20. A little bit of alterations to the schedule there. A ball is tossed up with a velocity of positive 29.4. It lands 6 seconds later. Find the velocity at each second. Remember that for every second that passes, we're going to change this velocity by negative 9.8. So at t equals 0, the velocity here is 29.4, and that's positive. But during this first second, it's going to change by negative 9.8. So that's going to end up being positive 19.6. After another second, it's going to change by the same negative 9.8. And so we add positive 19.6 plus a negative 9.8, and we get positive 9.8. After the next second, it's going to change by the same negative 9.8. So positive 9.8 and a negative 9.8 make 0. After another second, it changes by the same negative 9.8. And then another second, change by the same amount. And now it's negative 19.6. And then we change by another negative 9.8 during the next second, and we get negative 29.4. So from this, we can see that we threw it up with a positive value of 29.4. It lands with a negative value because it's going down, but it's still 29.4. The speed, the size of the numbers is the same. It's just that the sign is opposite because it's going in the opposite direction. So number 7, the velocity at the bottom is always the opposite of the launch velocity. Number 8, the velocity at the midpoint is always, well, it's 6 seconds, half of 6 is 3, and there the velocity is 0. It's always 0 at the very midpoint, the half time, or the very tippy top of the trajectory. Number 9, note that the acceleration is always negative 9.8. That's the acceleration due to gravity. And gravity is the only thing that's affecting the object in our toss here. We are ignoring any air friction or other possible things that might change the acceleration. Whether it is going up with the positive values, it's negative 9.8. At the very tippy top where the velocity is 0, the acceleration is still negative 9.8. And on the way down, when the velocity is negative, the acceleration is still negative 9.8. Remember, all of this acceleration, all of these changes in velocity are due to the force of gravity. Gravity is always pulling downwards, so the acceleration is always going to be negative. And the force of gravity does not change as we toss things up and down close to Earth here. And so it's always going to be 9.8, always negative going down. We'd have to throw the thing up miles in order for the 9.8 to change to something significantly different. And obviously that's not going to happen. Okay, let's go on to the next page. A cheerleader is tossed with a velocity of 7.8 meters per second. How long is she in the air? So we have the person here. They're being tossed upwards and they're coming back down. They toss up with a positive 7.8 meters per second for the initial velocity. We want to know the time for her to land coming back down. So we have VI. We want to find T. It appears that we don't know anything else. But actually, in the situation, there's a couple other things that we can write down, even though they're not explicitly written in the story problem. We know that for the whole time going up and down, the acceleration is negative 9.8 meters per second squared. And we also know that the final velocity is going to be the same as the initial, just a different sign. So it's going to be negative 7.8 meters per second for the final velocity. So that's all that we know and what we want to know. Let's double check our signs. We have the positive velocity going up initially, negative velocity coming down, acceleration showing the downward force of gravity at all times. So that's all good. The units, we have all meters and all seconds, so everything matches. It'll be fine. So the equation that will relate time to known things is going to be this. Final velocity equals initial velocity plus acceleration times time. Final velocity is negative 7.8. Initial velocity is positive 7.8. Acceleration, negative 9.8. And the time is what we're looking for. First step, subtract off 7.8 from both sides. And then we're going to divide both sides by 9.8. 15.6 divided by 9.8, 1.59. And that's going to be seconds. You can see a video of this being done, and it was one of the first viral videos that really made a splash in the internet age. It shows a cheerleader supposedly being tossed up and going through a basketball hoop before she lands on the ground. It looks quite convincing, but actually it turns out that when people have analyzed the video really, really closely, she passes in front of the basketball hoop and doesn't actually go through it. The net is rigged up in some way with a string or something to snap as she appears to go through. But you can see that by going through the link that's shown here. Number 11, see an exploding whale video. Again, there's the link if you want to watch it. Time the trajectory of the last piece of the blubber herd. Okay, what happened was that a whale got washed up on shore. It was dead before it got washed up. And people at first were amused by being able to go up and touch it and all that. But after a few days, it got to really, really stink. And so they got a city highway department to try to clean it up. And they couldn't haul it away, and nobody was willing to take the time to chop up a stinking whale. They didn't want to just bury it because they were afraid that the surf action would just unbury it after a few days and they'd still have the same problem. And so they decided that the highway department was going to take a bunch of their dynamite and blow the thing up to smithereens and hopefully blow the little pieces out to sea. Well, it didn't work. And so in class, we're going to listen for the bits of blubber that fall down on the spectators, and by timing it, we'll be able to figure out how high they went. Now, in this time, we're not going to take the effort to video this on this video here. We're just going to draw a picture here going up and down, and we're going to say that the pieces of blubber that we timed were 2.5 seconds after we see the explosion. And let's see how high these went. So the initial velocity, we don't know. The acceleration as it goes up and as it comes down, the acceleration during the entire time is negative 9.8 meters per second squared. And coming back down, we don't know what the final velocity is. So it appears that we have too much that's unknown, but there is something that we can say. We can say that the final velocity is equal to the opposite of the initial velocity, whatever it is. That's the key to solving this problem. So now, to find out the velocities, we can use this equation again. Final velocity equals initial plus acceleration times time. It's just that we're going to change this final velocity to be the opposite of the initial velocity. Keep the other initial velocity, negative 9.8 for the acceleration, and the time 2.5 seconds. Let's move the VI over by subtracting VI from both sides. So this is going to be negative 2 initial velocity is equal to, and then the 9.8 times 2.5 equals 25.4. I said that wrong. 24.5. Divide both sides. Divide both sides by negative 2. Then we get 12.25 meters per second. Now this isn't the time that actually came from the video. I'll let you watch it and time it yourself to see how fast or how long things were in the air. That's the end of the video. Next is a bounce lab that you can do when you come back to class. We can do that in the classroom whenever you return.